We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future? And how will they die? If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. This is the Milky Way, our galaxy. Approximately 12 billion years old, the galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars first and foremost. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years. This is how far light can travel in a year. Our galaxy's diameter is over 100,000 light years, and we're now located at a distance of 25,000 from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our own cosmic backyard and much bigger than Andromeda. But M87 is tiny compared to this giant. 6 million light-years across, IC1011 is the biggest galaxy ever found. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous. But why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.7 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time. So galaxies must have come from that very early universe and formed from it. For stars to form, and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together because to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble, the light we see from distant galaxies now. However, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots. They are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust, gas, and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source. And our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars, as far as we can tell. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations, like the Whirlpool Galaxy, then over billions of years develop into more orderly forms. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior. And they found out: a black hole. And not just any kind of black hole, but it's a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings, much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the sun, the stars also move due of gravity. What we discovered was a bizarre and violent environment. At the center of our galaxy, everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. So, is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light years. That's many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. So what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was in action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he grated on the astronomical community. And this is a brilliant idea. But he was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. And the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true, they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters, containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The 2 galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us, at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda as we know it will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide. But this age of galactic cannibalism will eventually pass. Because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities. We used to only know about the planets that circled around our sun. But now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun system. But now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are huge, rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star they're burning up. One thing is clear: no 2 planets are the same. Each one is unique, but most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So, at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with the cake. Then you'd put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way, depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. And these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then, it has enough gravity to crush it into a sphere. Any smaller, and it stays in irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things, like most metals, fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now, they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense. So it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were two effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal, rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials. But each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. And that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye, and you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So, radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens. As the Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then, big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry and there's not much going on. So why have the 2 planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only the atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So, not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field. And it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. And that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop. The flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere and the water evaporated. Mars turned into a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water, frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big. Because there was so much ice and gas, their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons. Some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside, far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995. Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely, gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So, how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the Sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So, water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So, it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain: there are billions of planets out there waiting to be discovered. Our solar system is a harsh environment. Volcanoes are destructive everywhere, from the ice volcanoes of Saturn's moon, Enceladus, to the immense lava fields of Jupiter's moon, Io, to our own planet Earth. It is truly true that we would not be here if there were no volcanoes. Volcanoes influence and alter our climate. Volcanoes are both the creators and destroyers of existence. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most potent natural occurrences on Earth. They create new land, destroy the old. They emit gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels bizarre new forms of life. Volcanoes help sustain life on Earth. Now we look for signs of life on other planets. We understand that life requires water. We are aware that it requires energy. And this is where volcanoes come in, as they generate tremendous quantities of energy. If we locate volcanoes on other planets, we may discover life. The search begins with this planet, which orbits the Earth closest. Venus, a planet that closely resembles our own. Venus and Earth have similar masses. Earth and Venus were very similar 3 billion years ago, with new land, new oceans, and an atmosphere. Both planets was conducive to life. On Venus, however, something went awry. Something caused the history of Venus to diverge drastically from that of Earth. Venus took a definite turn to the dark side a long time ago. Venus is hell, our malevolent twin planet. Today, the surface of Venus is like a furnace. The surface is 900 degrees Fahrenheit hot. It is actually heated enough to melt some metals, so you have no chance. Venus is a greenhouse world. Its atmosphere contains a high concentration of carbon dioxide. It absorbs solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot desolation. The planet was annihilated by dense CO2 atmosphere. The CO2 was produced by volcanoes. Spacecraft in orbit provided the initial clues. Radar broke through Venus's thick clouds and showed volcanic formations all over the planet. These formations look a lot like the shield volcanoes on Earth. Round and flat, shield volcanoes derive their name from their shape. These volcanoes ooze, but they ooze for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we began to examine its landforms and discovered that many of them were quite familiar. In particular, we observed enormous shield volcanoes that resembled the shield volcanoes in Hawaii. The radar images of Venus were identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were astounded to see a picture of Venus for the first time. We discovered a cratered volcanic surface. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of lesser ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. This could have been a home for life. It was instead consumed by flames. Numerous trillions of tons of carbon dioxide were expelled by Venus's volcanoes into the planet's atmosphere. The temperature rose dramatically. The oceans evaporated. On Earth, carbon dioxide is able to absorb into the rocks. It can be absorbed by the ocean. On Venus, however, there is no water, and the temperature is so high that carbon dioxide cannot even combine with the minerals. Volcanoes released carbon dioxide into the atmosphere eons ago, and as time passed, fewer and fewer methods existed to remove it from the atmosphere. Volcanoes sanitized the entire planet if Venus ever supported life. Earth is the only known planet with life. That may alter. This is the gas giant Jupiter, with its moons believed to be frozen and lifeless. A mystery surfaces as a cloud hovering over a cold and lifeless world upon closer inspection. On Venus, volcanoes transformed a planet similar to Earth into a hyperheated inferno. Volcanoes on a planet similar to Earth were not a surprise, but the discovery of volcanoes on the Moon was an astonishment. In March 1979, the Voyager 1 spacecraft provided us with our first up-close look at Jupiter's minuscule moon Io, a world we once believed to be frozen and lifeless. And they witnessed something odd. They observed this arc next to the moon, and it almost appeared as though there was a second moon behind it. We scratched our minds and asked, what could that be? Everyone is aware that Io is lifeless, dull, and uninteresting. And then people realized, oh my God, it's a volcanic eruption. We discovered that the area is engulfed in volcanoes. It is geologically extremely active. There are constant volcanic eruptions. And what they're erupting is a great deal of sulfur, which becomes extremely heated. And sulfur changes color as its temperature changes. It may be red, orange, yellow, or even black. As a result, these images of Io's visage resemble a pizza with various types of cheese and olives where the small black spots are. Io is not dead. It is alive and growing. There are more than 400 active volcanoes. The largest, Pelee, erupts from a gigantic lava lake. It extends approximately 400 kilometers into space. It would be an extraordinary sight if we could stand on the edge of that lava lake and observe that plume shooting off into the void of space. Pelee's eruptions are so massive due to Io's diminutive size. There is nothing holding the lava back, as there is virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes resemble fireworks. How can a moon so small be so volcanic? The answer is Jupiter. Similar to how the moon raises the tides in Earth's oceans, Jupiter raises solid rock tides on Io. The orbit of Io around Jupiter is not circular. Sometimes it's closer, sometimes farther away. Jupiter exerts a gravitational force on Io. Jupiter's gravity stretches and squeezes Io. In every 2-day orbit, the ground rises and falls by nearly 300 feet. This pummeling generates extreme heat and enormous pressure. Wherever there are weak spots in the crust, lava erupts. Volcanism is therefore planet scale. In contrast to Earth, where certain portions are active around the plates or in weak areas, this is an entire moon that's one active hotspot. Io is the most volcanism-active planet in the solar system as a result of the immense power of gravity. Volcanic activity on Io has taught us something new. It taught us that internal energy sources can drive volcanism in a manner distinct from that on Earth. Io is a lava world that is extremely hot and violent. It is difficult to conceive of anything surviving there. We have discovered strange eruptions on numerous planets and moons. But so far, the only world where volcanoes are linked to life is ours, or so we thought. This is Europa. It orbits Jupiter at a distance of nearly 500 million miles from the Sun and is a 2,000-mile wide sphere of ice. From afar, its surface appears to be polished. Up close, it's a different story. Europa is pummeled by Jupiter's immense gravity, just like its companion Io. The surface rises and bends, forming ridges and deep fissures. When we first obtained close-up images of Jupiter's moon Europa, they seemed vaguely familiar, and it turns out that they resemble Arctic ice flows. And it turns out they are the same. A global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements indicate Europa's ocean is an astounding 60 miles deep. The gravitational impact of Jupiter heating the rocky interior and melts the ice above. As the core is stretched by tides and heated, possibly melting, it is not preposterous to believe that there is a boundary between a hot core and a liquid water ocean. Underwater eruptions on Earth are surrounded by life. The same may occur on Europa. Here, the darkness is complete. The pressure, a crushing 2,000 Earth atmospheres. A harsh environment, but perhaps a cradle for life. If there is evidence of life on Earth, why not Europa? An energy source, volcanic activity, a universal solvent, liquid water, and a complex hydrocarbon chemistry are all present. Life would be difficult, but not impossible on Europa. There is life at every extreme on Earth, including searing heat, crushing pressure, and absolute darkness. Life on Europa may resemble our own in unanticipated ways. If life exists beneath Europa's ice, it would be aquatic, but without eyes, because there is no significant light. Organisms that essentially feed off the energy of the volcano would most likely utilize sonar to make sense of their surroundings. Volcanoes on Europa could be the genesis of new life. It is even conceivable that Europa is typical, that this is the norm for planets with life. Earth may represent an exception. Consider that Europa could serve as a model for the billions of moons in the universe with liquid oceans. So, all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. Our solar system is home to more than 170 moons. Multiply this by the size of the universe, and that's a lot of potential habitats for life. Only liquid water and a source of energy are required. Potentially, both are provided by volcanoes, and they are ubiquitous. This is Saturn, twice as far from the Sun as Jupiter. However, it also has volcanic moons, and similar to Europa, these moons could support life. Saturn is one of the odd planets in our solar system, with a 600,000-mile wide ring system, an astounding 62 moons, and one with a secret. Enceladus is one of the lesser and more distant moons of Saturn. And it's been known for a long time that it's covered in ice due to its extremely brilliant and reflective surface. However, when the Cassini spacecraft visited the planet, it made a remarkable discovery. Not on the planet itself, but on Enceladus did the Cassini probe disclose a remarkable discovery. A massive plume, backlit by the sun and erupting into space, is conclusive evidence of volcanic activity. Cassini's sensors zoom in on the south pole of the moon to capture these enormous craters scarring its surface. At the south pole of Enceladus, there are extraordinarily large fissures which open and close as Enceladus orbits Saturn due to the tides. Now, these fissures are enormous. They extend for hundreds of kilometers. And when they begin to open, you would see a large crevasse opening at approximately 100 miles per hour along its length. It'd be incredibly spectacular. Huge gravitational forces cause the surface to open and contract with incredible velocity. This helps produce the heat necessary to dissolve ice and form oceans beneath the surface. The conditions of the water beneath the surface of Enceladus are ideal for life. It is at the ideal temperature. It would be beneficial for life. Liquid water would be just like seawater here on Earth. And the chemistry of the water we observe erupting from these fissures suggests that it contains salt. It contains organic matter as well. Therefore, we have identified a location in the solar system where there is a strong possibility that there is life right now. In the ice particles, Cassini has detected complex carbon molecules. In conjunction with liquid water, they suggest that perhaps life could exist deep within this mysterious moon. Enceladus is possibly not alone. Another of Saturn's moons might also harbor life. Titan, one of the largest moons in our solar system, the only moon with a thick atmosphere, a frozen world, ice as hard as rock, lakes of liquid methane. Yet, we may also discover evidence of volcanoes and the tantalizing possibility of extraterrestrial life on this planet. Volcanoes are one of the most destructive forces in the universe, as evidenced by Io's raging conflagration and Triton's ice and nitrogen explosions. Even on Saturn's enigmatic moon Titan, however, destruction can lead to the prospect of life. It has a diameter of 3,000 miles, making it larger than Mercury. It has the thickest atmosphere of any moon in our solar system. There is weather, including cyclones, winds, rain, and even lakes, but the temperature is so low that liquid methane replaces water, and it's loaded with essential compounds for life. Titan has proven to be one of the most fascinating locations in the solar system. It's an active world. It is the only moon with a dense atmosphere, an atmosphere very similar to that of Earth due to the presence of nitrogen and, as it turns out, organic molecules. High in Titan's atmosphere, methane gas reacts with sunlight to produce compounds essential to life. But if sunlight consistently converts methane into organic compounds, why does methane not run out? Methane is abundant in the atmosphere, but we know that it is quickly eliminated by sunlight, so it shouldn't be there. There must exist a source of methane. Something on Titan emits methane in a continuous stream. Cassini has spotted what appears to be a crater. Infrared cameras disclose that the crater is surrounded by various types of materials. Scientists believe the green areas may be volcanic, possibly plains of lava ejected from Titan's interior. On Titan, the boiling liquid emitted by volcanoes could be either ammonia or water. Methane and ethane are emitted by Titan's volcanoes, and this is likely the cause of the planet's extremely dense cloud cover and orange atmosphere. This atmosphere likely originated from the outgassing of Titan's volcanoes. Even on a globe as frigid as Titan, volcanoes require heat. On Titan, there are two sources of heat. Radioactive substances heat the interior, and Saturn's enormous gravity caresses the moon, similar to Enceladus. These two forces produce sufficient heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan give life a chance to survive here? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide everything on Titan. If life does exist on Titan, it would be truly alien. It would breathe hydrogen instead of oxygen and possibly swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane. Possibly, there are tidal pools as well as volcanic and hydrothermal activity. Perhaps volcanic heat could produce enough energy to support life on Titan. That's a speculation, but it can't be ruled out. However, we may not need to travel so far to discover signs of life. We may discover it on Mars, a volcanism, rich world much closer to home. Volcanoes are ubiquitous throughout the solar system. Planets such as Io, Titan, and Triton are intricate, volatile, and violent. Once, we believed that Earth was the only planet with both volcanoes and life. Now, we find volcanoes everywhere, but alien life has yet to be discovered. Volcanoes exemplify the absolute force of creation and destruction. They go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. Volcanic cauldrons are the birthplace of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, replace the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times, when the solar system was immature on a planet similar to our own. This is the planet Mars. 3 billion years ago, volcanoes were active. The greatest volcano in the solar system still stands. The cliffs leading up to it are greater than 6 miles in height. Even Mount Everest would be comfortable in their shadow. This is the formidable Olympus Mons. It covers an area the size of Arizona. Its crater alone is 53 miles wide. A structure of this magnitude takes millions of years to construct, a period of time that volcanoes on Earth never have. The Earth's crust is constantly in motion. In the depths of the Earth, a solitary hotspot forces magma to the surface, creating a new volcanic island. While the hot point remains stationary, the surface is in motion. The new island moves away from the hot location and is replaced by a new volcanic island. Mars is different. The crust is locked solid. On Mars, there is simply no tectonic activity. The crust is one big solid plate, and so if there's a hot spot, it just sits there and builds and builds and builds. And you get a larger and bigger volcano. Therefore, Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era. Olympus, an extinct volcano on a fading planet, is now a veritable colossus due to Mars's diminished atmosphere. Hawaii, the ancient volcanic terrain of Mars, could one day support life. The evidence is readily available on Earth. Volcanoes on Hawaii have formed enigmatic tunnels known as lava tubes, which are formed when rivers of molten rock rush into the ocean. Lava tunnels are formed when there is an underground river of basaltic lava, magma, and molten rock at 2,000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface. It's the same, except here, the crust is solid rock and the river continues to flow beneath, creating this cave, this lava conduit. Recent images imply that Mars volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. Now, after possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This existence will be our own. Radiation will be one of the obstacles that future humans will face when attempting to live on Mars. And especially during solar cyclones, the incoming cosmic rays can be lethal. The tunnels and caverns of Mars's extinct volcanoes could one day serve as an ideal home, retaining air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new light. Volcanoes are capable of both destruction and creation. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that when miners in the Rockies came out of their tunnels, they thought the sun was coming up. So bright, in fact, that even at midnight you could read a newspaper. It didn't just happen in the US. People all over the world saw these auroras. No one knew why they had happened. But earlier that same day, an astronomer had seen something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed to have nothing to do with each other. But we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. And if this violent event happens again, it could destroy our modern technological world. The sun is the most familiar thing in the sky. It gives all life on Earth heat and light. It is so big that it's hard to imagine, and it makes up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and was made by the burning of hydrogen and helium for the last 5 billion years. But from an astronomical point of view, it's nothing special. A G main sequence star, also known as a yellow dwarf. But looks don't always tell the whole story. Solar flares and explosions of plasma, particles, and radiation from its surface travel far into space. We call this process the solar wind. Solar storms, on the other hand, are very violent eruptions. And a coronal mass ejection, or CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, we'll find out how bad a CME could be and what astronomers are doing to keep an eye on our star to try to predict when they might happen. Step back in time to 1859. First, in Victorian Britain, it was okay for a gentleman to be interested in solar astronomy. And one man did it in a very good way, Carrington Richard Christopher. We don't know what he looked like, though, because there are no known portraits of him. Carrington learned many important things from what he saw. He saw that different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body, but a fluid one. But he also saw that sunspots could be the start of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky in the morning. So Carrington was doing what he always did, which was to look for sunspots. He was using his telescope to project an image onto a screen. At 11:18, he saw two brilliant beads of blinding white light appear in what Carrington calls a kind of conflagration. Stranger still, they were gone after 5 minutes for no clear reason. Carrington had seen a coronal mass ejection, which was a huge magnetic explosion, a huge cloud of charged particles that are thrown off the sun's surface. After 18 hours, the Earth was hit by an electromagnetic storm. People started calling it the Carrington event. At the time, everyone was talking about the beautiful aurora, which could be seen all over the world. Even though a few telegraph systems went a little crazy because of power surges, it didn't have much of an effect on everyday life. Don't forget, though, that this was 20 years before the light bulb was made. That was in the past. Things would be very different right now. Coronal mass ejections are common, but they can be different sizes and move in different directions. So the question is, what are the chances that something like what happened in Carrington will happen today? And how would it change things? So, what is going on at the sun, on the surface of the sun, when we talk about the solar wind and space weather? The sun is made of magnetic fluid, and when that magnetic fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, which are called mass ejections. And these explosions are huge, sending out 1 billion tons of material at 1 million miles per hour. So, We want to know where these things are going because if they move toward Earth, they could affect the technologies we use. There's a very famous event in Quebec in 1989 where some power systems were disrupted for many hours in October. We've heard about the Carrington event, which happened in the 1800s. What would happen if it happened today, and how would it affect us? If we think about what we use satellites for now, we have GPS spacecraft that help us find our way, communication satellites, weather satellites, and even the stock markets are linked in some way. But we also have bigger power grids and a lot of wireless technology, and we don't know how they will react. How likely is it that something like the Carrington event could happen again? We know that the sun can still make these things happen. In 2012, there was an event that luckily didn't come toward Earth, but it did pass over one of the spacecraft we used to watch the solar wind. And it pushed all the sensors on that spaceship to their limits. So from what we've learned, we think that was at least as powerful as the Carrington event, and maybe even more so. It's just a coincidence that a big CME and one that's headed toward Earth both happened at the same time. And that's mostly just a matter of luck. We either get one or we don't. And how do we do with making predictions? Can we predict what the sun will do in a week, a month, or a year? Once a CME is up and running, we can start making predictions so that we can figure out how big it is, how fast it's moving, and most importantly, where it's going. All of this sounds very scary. Space weather is a problem, and the UK government knows this. The National Risk Register lists it. It's about as bad as a pandemic of flu. So, the people who make spacecraft are trying to find out what the most extreme conditions are in space, so they can make them so that they can handle those conditions to a certain degree. Both NASA and ESA are getting ready to send satellites into space that will get closer to the sun than ever before. The MET office's Space Weather Operations Center opened in 2014. It is one of only 3 places in the world that can predict the sun's effects on Earth around the clock. So far, the sun has had almost no sunspots, and the side that faces Earth is not expected to have any more sunspots or CMEs that are important. So luckily, there isn't much going on right now, and things don't look too different in the long run. So, spacecraft, satellites' power supplies should be safe for the foreseeable future. Trouble is, the foreseeable future in space weather forecast is, at most, just a few days. We still don't know a lot about CMEs, like where they're going, how big they are, or when they might happen in the future. 2 new solar probes will get closer to the sun than any other spacecraft has ever done. The Parker Solar Probe was supposed to be sent into space, and its destination will be close enough to the sun's surface to fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission that will measure the gas and magnetic field near the sun to figure out why this stuff is spreading out into the rest of the solar system. And this, the Solar Orbiter from ESA. Solar Orbiter might find out how sunspots, flares, and coronal mass ejections on the sun's surface are related to the solar wind. Solar Orbiter's success will be very important for our understanding of how the sun works. We think that the sun's magnetic field is made in a way similar to how Earth's is, but it is much more dynamic and changes all the time. We have an 11-year sunspot cycle during which the sun's magnetic fields move towards the poles and the polarity changes. On top of that, the magnetic field goes out into the solar system and flows over all of the planets. Solar Orbiter will measure these magnetic fields for the first time, and it will also give us the chance to watch the magnetic fields move to the sun's poles. To do this, Solar Orbiter will take pictures of the sun's atmosphere and measure the number speed, and temperature of the particles moving across the space between the Sun and Earth. But the magnetometer, which is made to measure the tiny magnetic fields in space that are carried by the solar wind, could be one of the most important and sensitive instruments. The Sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, who was the first person to record ACME, it was just a strange event. But now we know that these things can do a lot of damage to the world we live in. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejection will happen. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles or 6,052 kilometers, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock iron composition. Venus and Earth have a comparable structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles or 3,200 kilometers in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axis in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This is a phenomenon that isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. The solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles or 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there's currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, 96.5%, with most of the remainder being nitrogen. However, there are also traces of other gases, such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers. The troposphere, extending from the surface to about 40 miles up, the mesosphere stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles, due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers, about 12 miles above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle and arachnoids, circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet, and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus, using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system. Its vibrant stripes and prominent great red spot making it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones, characterized by lighter-colored clouds. Conversely, its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that's been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It's thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. The exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter, but also sheds light on the broader principles governing atmospheres, including our own. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is believed to have an ocean beneath its surface as well. As of my knowledge, cut off in September 2021, Jupiter was known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system. Although much fainter and smaller, Jupiter also has rings composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. Ladies and gentlemen, welcome to today's topic, aliens. Are they real? Do they exist? And if so, what do they look like? Today, we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Here are a few theories about aliens. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars, or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comment section below. Thanks for tuning in, and we'll see you next time. The universe is a vast and mysterious place, filled with countless wonders and secrets waiting to be discovered. Among the many mysteries of the cosmos, one of the most fascinating and profound is the age of the universe itself. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Scientists have spent decades studying the universe, using a variety of tools and techniques to unravel the mysteries of our cosmic past. Through their efforts, they have determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century, when astronomers first realized that our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927, but it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 1930s that the idea was widely accepted. Hubble's groundbreaking observations of distant galaxies revealed that they were moving away from us at great speeds, and that the farther away a galaxy was, the faster it was moving. This relationship, known as Hubble's law, suggested that the universe was not static, but was instead expanding. If the universe was expanding, then it must have been smaller in the past, and this realization led scientists to wonder just how old the universe was. The first attempts to estimate the age of the universe were based on models of stellar evolution. Scientists knew that stars undergo a predictable sequence of changes as they age, and they thought that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of stellar evolution, and they varied widely from a few million years to several billion years. It wasn't until the 1960s that a more accurate method for determining the age of the universe was discovered. In 1964, two astronomers named Arno Penzias and Robert Wilson discovered a faint background radiation that was present in all directions of the sky. This radiation, known as the cosmic microwave background CMB, is thought to be the leftover radiation from the Big Bang, the event that marked the birth of the universe. The discovery of the CMB was a major breakthrough in our understanding of the universe, and it provided scientists with a powerful tool for estimating the age of the universe. By studying the properties of the CMB, scientists could infer important details about the early universe, such as its temperature and composition. This information, in turn, could be used to estimate the age of the universe. Over the next few decades, scientists refined their measurements of the CMB and improved their understanding of the early universe. They also developed more sophisticated models of cosmic evolution, which took into account the effects of dark matter and dark energy, two mysterious substances that make up the majority of the universe. By combining these observations and models, scientists arrived at an estimate for the age of the universe, 13.8 billion years. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in cosmology, and it has profound implications for our understanding of the cosmos. The age of the universe tells us that our universe has a long and fascinating history, stretching back billions of years to a time when the universe was just a tiny, hot, and dense singularity. It tells us that the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. 13.8 billion years old. Why is it still expanding at an accelerating rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form, and what was the nature of the universe in its earliest moments? These are just a few of the many questions that cosmologists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand the cosmos, but it is just one piece of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the fundamental nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric known as space-time. This fabric can be warped and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. The age of the universe tells us that space-time has been evolving for billions of years, stretching and warping in response to the forces of the cosmos. It tells us that the very fabric of the universe has a history, and that the structures we see today are the result of an intricate interplay between space, time, matter, and energy. While the universe is expanding at an accelerating rate today, it is still unclear what the ultimate fate of the universe will be. Some theories suggest that the universe will continue to expand forever, eventually becoming a cold and dark place, devoid of stars and galaxies. Other theories suggest that the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the ultimate fate of the universe may be, the age of the universe tells us that we are living in a remarkable moment in cosmic history. We have the opportunity to study the universe at a time when it is still evolving and changing, when stars are still being born and galaxies are still colliding and merging. By studying the universe and its evolution, we can gain insights into the fundamental nature of the cosmos and our place within it. The age of the universe also provides us with insights into the likelihood of intelligent civilizations existing elsewhere in the cosmos. If life is a relatively common occurrence in the universe, and if the conditions for the development of intelligent life are present on other planets, then there may be many civilizations out there that are much older and more advanced than our own. Moreover, the age of the universe has implications for our search for extraterrestrial life. By studying the conditions that led to the emergence of life on Earth, and by exploring the diversity of life forms on our planet, we can gain insights into the types of environments and conditions that might be conducive to the emergence of life elsewhere in the universe. Some theories suggest that the universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe tells us that if a multiverse does exist, then there has been ample time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of the cosmos. From the cosmic microwave background radiation left over from the Big Bang to the intricate dance of stars and galaxies across the night sky, the universe is a rich and complex tapestry of phenomena that is both awe-inspiring and humbling. In conclusion, the age of the universe is a remarkable fact that has profound implications for our understanding of the cosmos and our place within it. It tells us about the origins and evolution of the universe, the potential for extraterrestrial life, the nature of reality itself, and the beauty and wonder of the cosmos. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information, guiding us in our quest to understand the cosmos and our place within it. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space, from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch. The subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms. Protons and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic dark ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. A supernova is the largest eruption ever observed by humans. Each detonation is the incredibly brilliant and incredibly powerful outburst of a star. One variety of supernova is caused by a dying massive star's last effort. This occurs when a star with at least 5 times the mass of the Sun explodes with a tremendous explosion. Massive stars consume vast quantities of nuclear fuel in their centers, or cores. This generates enormous amounts of energy, causing the center to become extremely heated. Pressure is produced by heat, and the pressure produced by a star's nuclear combustion prevents the star from collapsing. A star maintains equilibrium between two opposing forces. Gravity attempts to compress the star into the smallest, most compact spheroid possible. However, the burning of nuclear fuel in the star's interior creates a significant outward pressure. This outward thrust resists gravity's inward compression. An enormous star cools down when it runs out of propellant. This results in a decrease in pressure. Gravity triumphs and the star collapses abruptly. Imagine something with a mass 1 million times that of the Earth disintegrating in 15 seconds. The collapse occurs so rapidly that it generates immense shock waves that cause the star's outer region to erupt. Typically, a dense nucleus and an expanding cloud of hot gas termed a nebula are left behind. A supernova of a star greater than approximately 10 times the size of our Sun may leave behind black holes, the densest objects in the universe. Think about being an astronomer at the start of the 17th century. As the telescope has not yet been developed, you must use your limited vision to explore the universe. Then, one day, you see a truly spectacular scene. In the next several weeks, a new star will shine brighter than Venus. Very high levels of brightness make it visible throughout the daytime. As the months pass, it fades somewhat but persistently in the sky. Skywatchers across Europe, the Middle East, and Asia all witness the same thing that the German astronomer Johannes Kepler did in 1604. Now we know it was a supernova explosion, a massive explosion that occurs when certain stars approach the end of their lifetimes, and not a new star. The latest supernova to occur within the Milky Way was in 1604. Maybe more nearby supernovas have occurred since then, but they have been veiled by interstellar gas and dust, and hence have not been noticed. The Crab Nebula is an example of a remnant of a supernova that occurred thousands of years ago. Its light reached Earth around 1054. The supernova discovered in the Large Magellanic Cloud in 1987 was the closest thing to Kepler's supernova in recent years. In addition, several supernovae in other galaxies have been documented. These may be seen with the naked eye, but only with a telescope. Skywatchers in Kepler's day would have missed them totally. Hence, it has been 418 years since we last witnessed a star explosion in our galaxy. Is a close, brilliant supernova therefore long overdue? Scientists predict that between 1 and 3 stars should burst in our galaxy per century. If the next supernova occurs, modern astronomers will be better prepared for it than Kepler was, or even scientists from only a few decades ago. Astronomers now have access to telescopes that can record visible light. When used together, these equipment will simulate the experience of flying near to a supernova and observing it with our own eyes. In addition, we have telescopes that are sensitive to infrared light, or light with wavelengths that are beyond the red end of the visible spectrum. Infrared light, with its longer wavelengths, may penetrate gas and dust more easily than visible light, allowing us to see objects that might otherwise be hidden from view with conventional telescopes. Examples of instruments that predominantly record in infrared include the James Webb Space Telescope. The electromagnetic spectrum includes both visible and infrared light. However, neutrinos, which are subatomic particles, are also emitted by supernovas, and modern detectors can capture them. Also, astronomers now have detectors that can record gravitational waves, which are tiny vibrations in the fabric of space-time thought to be released by exploding stars. In the scientific literature, 2 kinds of supernovae have been identified. When a white dwarf star undergoes a Type 1 supernova, it sucks material off of a partner star until a runaway nuclear reaction occurs. causing the white dwarf to be blown apart and send debris hurtling into space. As a star runs out of nuclear fuel, it collapses under its own gravity and bounces, setting off an explosion known as a Type II supernova. There have been instances of both types of supernova being brighter than their host galaxy combined. The tremendous amount of neutrinos that are released alongside the light makes Type II supernovae very fascinating. Neutrino emission can actually begin before the explosion happens. Even though the field of neutrino research was in its infancy when the explosion of 1987 occurred, 3 detectors were able to record a total of 24 neutrinos. One may expect hundreds, if not thousands, of neutrinos to be recorded by the global network of detectors should a supernova burst within our galaxy at this time. Very provocative signals might be produced in the event that a falling star forms a black hole, therefore preventing the explosion from producing any further stellar debris. In those conditions, the neutrino stream would abruptly cease. It would be awesome if you could see the black hole's sharp boundary, which indicates its formation. The missing star might then be identified by comparing it to other stars in astronomical databases. A lost star might be the site of a freshly generated black hole. Successful discovery of gravitational waves from a galactic explosion would round off the hat trick. Gravitational waves, which Einstein said would exist when a huge body was accelerated, are distortions in space-time that are produced as the mass of the body accelerates. Such signals were identified for the first time in 2015. Black hole and neutron star mergers are responsible for the gravitational waves seen so far. Yet, when a supernova does occur in our galaxy, it should also be seen. Computer models of supernova explosions have been used by astronomers for decades, but many features remain unknown. Knowledge gained from studying gravitational wave data may shed light on the method. What danger may a close supernova pose to life on Earth? In principle, yes, but the explosion would have to be quite close, since there are currently no nearby stars in danger of exploding. To be sure, a close supernova's radiation outburst would be disastrous, so this is excellent news. The explosion would release harmful UV-X and gamma radiation into space over a period of weeks, damaging Earth's protecting ozone layer, even if they didn't reach the ground. Without the ozone layer, the sun's lethal UV radiation would flood the planet, killing everything from phytoplankton in the oceans to humans. It's possible that something like this occurred sometime in Earth's past, around 360 million years ago, near the close of the Devonian epoch. A massive extinction may have been caused by a supernova. On the other hand, supernovae are not just destructive forces. They may also give rise to new life. Astronomers and physicists point out that the nuclear processes that take place deep within exploding stars and spread throughout space as a result of the blast waves they create are the source of many of the heavy elements on which humans depend. This means that a supernova would be the new gold standard for astronomers. Thanks for watching. Hope you enjoy it.